Okay, we're good.
Okay. So we're going to be talking a little bit about how to get performance. Some of this should be a little bit of review. Hopefully we'll be able to talk about some application areas it goes and some general difficulties with this, and we'll kind of lead into where, for parallelism, this is going to matter for us. So let's kind of start off with some of the basic areas. There's two ways that we can measure performance. Anybody remember what those two ways we can measure performance in the system?
Well, I think that was throughput.
Okay, we have throughput.
Time.
And time. So if you think about these, there's kind of an analog to what's going on. When you're dealing with time, we're measuring in, seconds or whatever else is going on. What's throughput a measure of? Unit-wise.
Stuff you get done over time?
Yeah, so it's like tasks or activities over time. So we can just think of this as typical time. Really what you're dealing with, if you start thinking about this, is this one is your time domain and this is your frequency domain of what's going on to it. And this should not be in some way surprising in an engineering context that some of our problems are easier to formulate in time and some are easier to formulate in our own frequency space that goes on. So there's an analog that goes on to a lot of other of our designs that happen. Now, when we're dealing with each one of these, time we generally tend to talk about as a latency issue that's going on. So this has to deal with, does a particular path line or a particular calculation, doesn't matter when it finishes, as opposed to how much work is happening or anything else. So if you think about like a scientific computation, if I need to get the solution to a problem, I launch the problem, what matters to me is when does it finish. So like a lot of the medical imaging stuff I'm doing, the doctors could care less about anything involved other than how fast do they get their picture. So in that case, the measure that matters to the problem is a latency measure, it's time. Now, when you're dealing with throughput, what you're caring about is if your metric is going to be measured by how many things can go on simultaneously. So this one often hits when you're dealing with large servers or web services or things of that sort. If you imagine for a sec you're Google, right? If somebody has trouble connecting to Google and they're just denied, right? But you're able to get other places, you're going to think something weird about Google. But if your connection to Google is slow and it takes a while to get your answer, who do you blame? You're gonna blame your ISP, the internet, whatever else. You're not gonna blame Google. So latency is unimportant because they're not gonna get flagged if it takes a long time to get your answer. But if you get a server denying connections, then you're gonna be like, what's wrong with them? Aren't they maintaining things? They're gonna get a very high hit. So what they wanna do is let you in and then take a darn long time if they need to. That is the economic reality of the situation. So they care about how many users can connect simultaneously. Throughput is what matters. Similar types of things happen when you've got database services and everything else that goes on. People will tolerate an awful lot of latency, but they won't tolerate I can't connect. Right? So you've got to look at those problems and see what is it, because it constrains some of your solutions. The reason why we look at performance is because before we do something, we want to know if it's going to work. Because you don't have enough time to tackle every problem. So you have to see in advance, how likely is this to actually bring about my solution? So let me ask you a question. Are there things, if I improve time, say I do something to make the system just purely faster, takes less latency, will that help throughput?
Yes.
Absolutely. Think about this, right? If you're trying to deal with how many people can connect in a second and how fast I can process your connection, it takes half as long now. That means in that same second I can handle twice as many connections. This is kind of the nice thing. You increase your performance in this area, you will get a corresponding increase in the other. Is it reversible? If I increase my throughput, will I decrease my latency? This is the weird one, okay? But here's the easy way to think about it. Imagine I want to increase the number of people who can connect to my service. So I put in an identical server that is going to, will just automatically split and route half the people to one and half the people to the other. So I've got a backup server that's going on to handle these. I can now process twice as many people. Does it take less time?
No, and it may take a slightly longer time.
It might actually make it worse. Right? As a matter of fact, a lot of the things we do to improve parallelism, we often just talk about how much it speeds it up when everything's working perfectly, but there is actually a little cost. When we, for instance, go in and do pipelining, in order to do pipelining, we have to put in buffer registers between the stages. That's an extra register that has to go in. That register takes time to access. So we don't usually emphasize this, but the pipeline actually has worse latency. You'll get more stuff done in that same period of time, but an individual command is actually going to perform worse, even though a whole ensemble of them will perform better. So the sad thing is that throughput often will worsen time, and time will improve throughput. Now, sometimes throughput is the right one to do. If that's what your problem is, then you don't care what happens on this other side. Do what you need to do to make that one work. But if there's any question, time always makes things better. You're not always able to get the improvement you want out of that. But if you can make those type of improvements, it is an across-the-board help. So that kind of gives you at least a little bit to think about these. All right, for a program, we have ways, and we'll talk about the timing on these that we kind of do to predict for hardware. But realize when we calculate this time, you will not achieve that time. So this is kind of the next equation, right? We always present it on the first class, and boom, here it is. But here's reality. Do you think you will ever see that time? What will stop you from achieving that time on a computer? You're the only process running? So let's assume that I can perfectly predict how long it will take to run your fraction of it. The OS has to run. There's other processes. It's going to swap you in and out. It's going to, in order to swap you in and out, it has to move memory around to make those things available. So there's a lot of other things that are going on in your system other than your actual process. That's why when you're trying to measure performance, you never ever run the program once and see how well it does. That is completely unrealistic. Because how do you know that the OS didn't happen just trigger a cleanup at that instant? So when you're doing them, we usually run it several thousand times at the same area to get a good performance metric, and we average them. And the assumption is on that one that you're at least going to get, even if you might not get the pure performance of your program, you're going to get the best number you can get about how your system will perform on that computer. Because the OS and other things happening and everything else is part of reality. Now, we usually try to stop other processes and everything else, mainly because we want a good number for our system. But it also does improve performance, and that's why an isolated system is going to get you your best performance on it. But when you're thinking about those, realize we're calculating this time equation. We're assuming you're the only thing running. That has not been true for over 30 years. Right, and even then it was pretty questionable. So, you know, you got to keep in mind where those ones go on as it's happening. So this is a somewhat fictitious measure that's happening. But it at least gives us a ballpark. And the real reason or benefit to this one is that if you can show your hardware performance would increase this, it will commensurately increase reality, even if it won't give you the actual number. And if you show an improvement here, you should see an improvement in reality on average, because all those other things would be there one way or the other. So what this equation allows you to do is to assess a hardware change or a software change and get an idea of what type of improvements you should get. So So don't use the time equation on this to actually expect that time. Lower value of the time, yes, but it's a best case scenario, right? But the ratio should at least give you something. That's kind of the first area that we go. Okay, anybody remember how we calculate time? So think about what has to happen on a computer. When we're talking about time for a program to run, it has to do a certain number of instructions. So let's call that the instruction count that's going on. I've got a certain number of instructions. Now, does every computer, do they all have the exact same hardware? So some people have tuned their hardware to work for certain types of instructions and some for other types of instructions that go on. Now, we're just talking on average at the moment, and then we'll get more detailed in a sec. Right? On average then, we'd expect that one instruction, how long would it take to run through that system? That's a useful idea then, because we've got to somehow convert number of instructions to time. So if I knew how long one instruction took, I could convert, right? Well, we can't get an exact time because every system has different clock speeds and they have different architectures. So we're going to break this into different numbers we can do, right? If we understand the hardware and we look at it, we can see it can process how long in cycles will it take for one instruction to go from start to finish. Now once we go to RISC, this even will change a bit, but let's just take this one for the moment. Look at the hardware from when it has to start fetching to when it writes back into the registers. We can look and see, oh, how far does it have to go through? How many cycles is it going to take? So we can figure out how many cycles per instruction. So if I multiply that by the number of instructions, I've now got cycles. That make sense? It's just units. Instructions cancel, I've got cycles. Right? That means that in order to get time, I have to multiply by seconds per cycle. And then cycles will cancel and I'm left with seconds. Make sense as a goal? This is what physicists call unit analysis. It's extremely useful as it goes on, even for us as it's going through. So, how do I get seconds per cycle?
1 over the clock frequency?
Yeah, because that's cycles per second. So that's 1 over f. This right here is cycles per instruction, so we call that CPI. It's just an abbreviation of exactly what the equation is. All right? And then we're going to take this, divide by the frequency, and multiply by the instruction count, and there you go. You will sometimes see that 1 over f is sometimes multiplied by the cycle time. Because if you just multiply by how long one clock frequency takes, right, one cycle takes, then that's also an acceptable measure. But most people know f, so I tend to express it in that way. Okay, this will give us a pretty good measure. Now, I've already alluded to one of the problems here. This is an average CPI. That means that we're treating a logic expression like a NOT gate the exact same way that I would do a memory access that has to go to the hard disk. Okay? These are clearly very distinctly different things performance-wise as it goes. And what we've done is we've taken an average. But averages have to be based off of a simple equation. Right? Anybody remember how we calculate averages?
Add up all the values and divide by the number.
Okay, so that's the first one that we do. There's an assumption involved in that, right? So I sum up all these x things, right? I equals 1 to n of x of I, and we divide by n. What's the assumption?
That your instructions in that case are evenly weighted.
They're all even. We're assuming that the whole thing, everything is basically the same, it happens the same amount.
Yeah.
So that means I do the same amount of logic instructions as I do additions, as I do memory accesses, as I do branches, that they're all exactly the same. Do you think that's true? No. What do you think is the most common instruction that we do in a computer? That is a very common instruction. But on a typical one, we can actually get something even more common.
I don't wanna say no on it, it's bad.
Let's hope not.
I'm thinking Windows.
I can actually do you move by an add. Add 0 to it, send it to its destination. Every time you do a loop, you almost always have to do this for it. When you check if you're done inside a loop, that's subtraction, which is using the adder unit, because it's an adder subtractor as it's going in. So every time you check anything, anytime you increment anything or have a loop or a counter, just go through this. So you're doing it for your branches, you're doing it for loops, you're doing it for, just think how many times those type of instructions go through, let alone just appearing as part of your equations, how often addition comes up. That adder unit is normally just disgustingly commonly used. So often arithmetic, which the general family that's lived in, is anywhere from 40 to 60% of your instructions. Right. So that's a really pretty heavy area. So technically speaking, your move is actually in here. Right. Now, depending on how things go on other ones, different types of instructions that are out there could have different weights. And these can actually even be used to assess how good of a programmer somebody is. One of the most common metrics used is the humble branch command. We can examine somebody's code, and as long as the person wasn't deliberately trying to alter this metric, they were just coding naturally as they would, how many branches or what percentage branches ends up in your code is a good measure of how good of a programmer you are. So on a typical situation, a really good programmer is going to have around 15% or so. And a really bad one will have around 25%. So this was actually used for a long time in Silicon Valley until programmers started discovering, oh, if I stick useless branches in there, it'll increase my fraction and I'll get a pay raise even though I'm producing garbage code. So, when people discover something, they'll always find a way to abuse a metric. But the reason why this one is so important is it's very hard to schedule efficient code with too many branches, because branches are always a little bit tough. Because which way does it go? So now the loading, so now you have to rely on speculation and prediction. So when you're dealing with this, you really ideally would like your loops to be big enough so that it's easier to schedule things and move things around and pack it efficiently on a multiprocessor. And a good programmer will think about the system they're working on and figure out how to make it easy to get efficient code placed. So, this tends to be where they end up going because they then try to aggregate things and don't just write the first thing they think of. Now, that being said, you should write the first thing you think of and then tune it. Right? This is the other thing that goes on. A good programmer is not going to waste time tuning an irrelevant portion. So make sure you only tune the stuff that needs tuning. If there's a piece of code that's used once, it really doesn't matter if it takes a little bit longer. Something that's inside a loop and is going to be used thousands or millions of times, now it really matters. So you want to adjust those as it goes. Now, the other reason why branches are important is because they're slow, which I've alluded to, that you have to predict them. Do we all remember the MIPS pipeline? It's not the only one out there, but most people have based their stuff pretty similar on it because it was a foundation one. It's a 5-stage pipeline as it goes on. And we first fetch the instruction, and then we have to decode it, figure out what is the instruction, get the things available to do your calculation. Then we're going to execute, do whatever that is. Then if you need to, we're going to go to memory, and then we write back and update whatever's inside those registers. Now, when you think about these pipelines, let's say time is increasing this way, so here's 0, 1, 2, 3, put in some lines breaking up our time, okay? If my branch comes in here at the first time instant, For a pipeline, every one of these stages, there's buffer registers, so I can keep them separated, so that I can reuse parts of the hardware to go in. So at the next instant, when the branch is here and I'm figuring out what it is, this is the first time you'll know it's a branch. I'm loading in some instruction. What instruction do I load?
The next one's sequentially.
Okay, so I've got a piece of code here that looks like branch, and I've got x1, x2, x3, and let's say the branch is jumping somewhere else inside the code. Maybe I'll put down here, y1, y2, so on. Right? So the easiest thing to do is to load x1, x2, right? It's right there. What do you think is most likely? I've kind of framed this one up as an if statement, and I'm perfectly reasonable to look at this as an if even for likelihood.
Sort of.
You think it's 50-50?
Yeah, it depends on your program.
It does depend on your programming a little bit, but not as much as you might think. What's the most common thing that you're testing for inside of a system where you're going to do an if?
An error.
Okay, so you're looking for errors. That's probably your most common. Some needed a data entry error, right? Those ones are really common. At the beginning of any code block or subroutine, you should always check to see, am I getting what I expect? How likely is it that you're going to get a problem?
Hopefully small.
It should be small, right? I mean, by design, you're catching that 1 in a million type of error, but realize what does that mean percentage-wise? That you're going to run this code versus this section. Right? I mean, if this is really infrequently, even happens 1 in 1,000, it should be very unlikely that this code runs. So when you're doing the error checking, what's inside is really infrequent. How about if I'm not doing error checking? Right? What if I'm just inside a loop and I'm, checking on these and maybe I have a breakpoint to cut out? And yes, everybody says you should never cut out doing that. That's spaghetti code. And yet, however, it turns out to be more efficient time-wise. So I'm not saying whether it's pretty code or not, but it is more efficient code. But I could have something even inside a loop that could be checking, am I done to set a flag, right? To make it look a little bit nicer in that sense. How many times will you go through that code checking to see has it reached its conclusion versus how many times do you find that it's hit its conclusion? Probably a lot more likely that it doesn't, because the second you find the conclusion, it exits. If you start looking at the times you actually do checks, most of the time you check in nope, 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 yeah. So it's extremely more likely that you are going to branch when you hit a branch than it is that you're not going to branch. Right? That may sound really odd, but it is extremely true when it's going in. In pretty much any type of instruction. You think about a regular loop at the bottom, should I go back up to the top? Right? Maybe you're going to loop through it 100 times. So you go up 100 times, you drop out once. You can, if you start thinking about this for a sec, it's really likely to run down here. It's not very likely to run here. But the easiest thing is to run that. So if I load x1, there's a decent chance I'm wrong. So this is where branch predictors come in that's going on. And we try to predict which one it is. And in general, we want it to actually pull y1 in next. But how can I pull y1 in if I don't even know that it's a branch? Is that even possible? It is. Yeah, everybody stares at me strange, but this is prediction, right? This is one of the things that I really loved about this from my estimation side. I can absolutely tell that's going to be a branch instruction before you load it. Not the first time. But I can absolutely do it afterwards because I get profiles of your code. And I can store profile information about what was at that address before. It probably hasn't changed because your code shouldn't change while it's running. So I can store profile information, and we often will for, say, like a block of 1,000 instructions at a time. And we'll look it up, and we'll store whether it was a branch or not, and what the destination address was, and even sometimes what the instruction was there. And we can load out of that profile storage, we can load the next instruction. This is called speculation. Okay? So speculation, what we do, the first time you run it, you cannot do anything with it. But it just keeps storing data. The more data I have, the more likely I can say, hey, I can go in and take advantage of this previous information. And if I don't have a lot of data on you, then commensurately, yeah, I can't do anything on the first time, but it's probably because either we're very early and I'm gonna get a lot of benefit later, or you're just not very important, it doesn't run very much. In which case I don't care that I'm not getting a performance increase on it because it's not an important section of code. So commensurately, speculation gets better and better for code that runs frequently, but that's the only code we care about. So it's actually a really nice feature on it if you start thinking about what's going on in there. So doing speculative instruction, and we'll talk later, one of our topics will be on this. How do we build such a system? But I want in your head the idea. So when we hit those spots, you can start thinking, hey, what can I do? How can I make this faster? Because there are some areas, if we can make common cases get down where we're getting 0 as a latency delay, all of a sudden this becomes a very important instruction. And branches are, you know, a pretty decent portion of my code. All right, so, but here's the problem. Inside of our system, let's assume I stick with exactly what we had before. When do you think I can tell you whether the branch should have gone to clear the pipeline out? So decode, I figured it out. Now we're not assuming I have a speculation system or anything. So I'm just having to go through it. This would also be when do I find out if my speculation was correct or not. All right? So decode, I figure out that it is an instruction, but I just got the data to check, so I haven't been able to check it yet. In execute, there was a condition with my branch. So in execute, I check the condition, I get the answer, but have I been able to set the system yet? And so it happens here. Now the question is whether or not X3 loads or whether I can get Y1. And this depends how fast, how early into this I can get something going. And whether or not this needs to know its answer immediately. On the standard MIPS pipeline, it's one logic gate here. And they allow that directly to be rerouted, if necessary, right into your memory port so that you can load the next instruction and I can get Y1 if I needed it. But if you did, that's a speed up area again. If I don't hit that, I might have X3, which means I could have up to 3 instructions that are wrong in my pipeline that I might have to dump out. So that means this branch had its own base cost plus 3 more bads if I'm wrong. And if you guess next, you're probably wrong about 95% of the time. But it is the quickest, easiest thing to happen. So an awful lot of systems do it. And once you get to smaller embedded systems, it's pretty much guaranteed they do that. Right? So, you know, performance and what's efficient start going counter to each other. But do we see where the areas go? This is why we care about the performance metrics, because we want to look at these and say, hey, that section is holding me down, what do I do to fix it? Now we know what we have to do to fix it, and we can see it right with the instruction. So branches have a different percent, and they have a pretty big penalty. What's the worst instruction you can ever do? Memory. Now, memory was good enough when we were dealing with, you know, the first course in this. I want to get more specific. There's 2 types of memory as instructions. Loads and stores. Which is worse? Because it turns out one's really bad and the other one's not really bad. It's mildly bad, but it's not really bad.
Store.
So I'm going to go for store is bad. I'm going to go for load is bad. Only one. So if we were on a game show, you would definitely not go with him. But load's the bad one. Here's why. think about what you need when you're doing these operations. If I'm the CPU and I'm saying store, right? The CPU is the fastest part, and it's kind of like, you know, your CEO or whatever. Your CEO has a whole bunch of assistants, vice presidents, whatever else, that are, you know, a CEO can then assign tasks to. So if you've got something to store, right, our CPU has cache as an assistant. So our CPU can go to our CPU's assistant and say, cache, store this for me. Now, does the CPU need to know that it's been stored before it can move on? You don't, do you? You just need to guarantee it's going to happen. Right? And if something goes wrong, it needs to be fixed, but you can still keep on going. Let's say you're loading something. Why are you loading a variable?
So you can use it.
So you can use it. So can you continue on if you don't have your data yet? No, you are stuck until the data comes. No matter how many assistants you have or anything else, you are blocked until you get your data. So you have to wait for it. So this is the first cut. Stores often will have almost no penalty on a good system, because what they'll do is they'll just shove it down to cache, and cache will have a buffer on there called a victim buffer that goes on. You know, if assuming it has to write all the way down, or if it's already in cache, it'll just update its cache value and be done with this. So if it's not there, it puts it in a buffer to write it down when it gets a chance. And if it is there, it just updates the value and it's done, and the CPU didn't slow down at all. So this often has no penalty. Now, if it ever gets to the point that one of those buffers fills up or something, cache now has to signal, hey, I can't handle your request. Now it stops. But that's rare. That can, I mean, you can literally go millions of cycles before that happens. So this one is not a big problem at all. This one is a problem every time you do it. How long does it take to access RAM? Right, we always say it's 50 to 120 nanoseconds, somewhere in that ballpark range that's going on. Okay? Now here's the fun part. That number is somewhat of a lie. Let's take 50 nanoseconds. 50 nanoseconds, that's the time to access that cache. Totally true. But when you do a write, you access the cache and the value in the cache has been updated. How does RAM store things? Anybody remember the technology we use? It's called DRAM. Anybody remember what's DRAM? Dynamic. So how does it store the value? Charge on a capacitor. So for a write, I put charge on the capacitor to go on. Let's say you did a read. What happened when you read the value out of that memory cell? You discharged the capacitor. So guess what you now have to do? You have to charge back up, store back. So when you do a read, it actually takes double. Now you can send the answer halfway through once it's accessed it, but RAM is going to be out of commission updating things for a little while. There are ways to speed that up. But that involves cache on the RAM chip that will now hold it, and you read it out of a SRAM buffer, and then you update in blocks. But in general, when you do a read, number one, you have to wait for it, and number two, it takes twice as long. Read, write. So this is really painful. We put cache in, we'll try to cut it down and everything else. We'll talk about performance increasers and things of that sort. But you need to keep in your mind where the problem is and how big of a problem is it. So there are simple ways to solve this one. This one is a challenge. So we'll spend more time there. Now, percentage-wise of use, how do you think they split? Which one do we do more of? Yeah, this is, you know, depending on the code, it can be anywhere from, you know, similar to branches, 15, 25, sometimes even 30%. This is usually down around 5. So, It's a big advantage, anywhere from 3 to 6 times as much on the load side. So, I mean, fortunately, we've got lots of problems to fix. And I do say fortunately because if there were no problems to fix, then we don't need you. Right? So, I mean, when you see a problem, be happy. It's a gift. Right? All right. So that means that I can't do this type of thing because they're not all equal. If you notice, there's radical differences between my fractions. And the commensurate things I'm averaging are very different, so I can't just lump them together. So now how do I do it? Wait. Yeah. So if you think about it, this technique for doing them, I could pull this 1 over n in. That's the same exact formula you had before. But now you can see what it's assuming. We're assuming that that particular type is 1/n of all instructions. Right? So we're making a prediction about what the weight was, and we're saying it's equal. Well, if they're not all equal, then I have to just put what that weight is. And that weight is going to be your fraction. How often does it get used? Therefore, that means the sum of the weights had better equal 1. That's just saying the probability had better add up to 1 on everything. Or when I'm saying I'm getting fractions, I shouldn't end up with 110% of my instructions. People love saying I give 110%, but they really don't. Right? You can't give 110%. You know? Yeah, I'd be happy if somebody gave me 95. I mean, that's just, I mean, as a person, you can't do that. So, but on ours, it had better add up to 1. So that means some of them might not be perfect because your fractions are not going to be even, but that's how you're going to get your weights. When we split these ones out, that goes on. So this is now how you are calculating that. I can separate that. So now I have the instruction count, the sum from I equals 1 to n of Wi times the CPI of group I, whole thing divided by the frequency. That's what we're dealing with, where this is the fraction of the commands, and that's how long that one takes going through. This, for a particular type of instruction, you can look at exactly the path it's going to take through, so you can predict that. You can look to see what type of hardware there was in there, and therefore how it will change that number. So you can get down to pretty good brass tacks with this. Most of the time. Sometimes these numbers will still be averages. Because it might rely on a piece of data you don't have just looking at the circuit. Right? Branching and memory are 2 great examples. For branching, it's not just what circuit it flows through, it's also, were you right or wrong on your prediction? But right or wrong is going to depend on the actual running data, so you won't know until the program runs. So you can't predict it in advance. Right? You can take reasonable guesses based on profiles of what have happened in the past of running programs, but you can't say for certain. So that CPI is still going to have to be a weighted average of expectations. Memory, same thing, you're going to go cache. You can't guarantee until the program runs. Now, there's a second half is that once the program runs, I know what happens. The reality is, when you look at a running program, you run the same exact code on the same exact system, one after another. It's going to run radically different. And I do mean radically different. So, when you're considering these ones as it goes, don't assume that's going to be a perfect example of what's going on. It'll give you a good idea, but the ensemble will carry it. One time a certain area might run a little more efficient. It might load the cache slightly differently. It really does not do the same thing every single time. Your code doesn't even run in order. That's what the project you guys are building is on, how to build a system that runs out of order. The system you're doing is a basic Tomasulo's machine. Tomasulo invented that algorithm in 1960. Right? So you're working off a thing that is 55 years ago. We figured out how to run code out of order and still be able to maintain the answer. So that is still kind of the basic idea, and everybody does variants of it, which is why it's a good solid base to work on. but realize there's a ton of little tweaks. Since it can run out of order, it's gonna grab as best it can what it sees as the best opportunities to reschedule things. So you can't even guarantee your code's gonna run the same order from one run to the next, let alone that it's gonna take the exact same time. But on average, you can talk about those. So those are gonna come down, yeah.
So if there's that much variance in the timing equation, why not just determine everything stochastically, so you can take your cycles per instruction and then plot it along the distribution, find the expected value, and then you can just have a confidence interval for.
And that's what I'm actually arguing we do,
Okay.
right? And so we try to break it down specifically when it might open up a portion. But then even once we get to that, my comment to you is, it is so distributed, you can't always guarantee that sub number. I've now broken this down to at least a meaningful class. And it's meaningful because I can change the hardware at this level, right? And so I can look and I can see hardware, but this is still going to actually require an ensemble to take a look at what's going on. Because you're not gonna see the same type of data running through it every single time. So you've gotta take a look at how that improvement's gonna handle on average. Does that make sense? So yeah, I mean, you've got the exact idea of what's going on, and we will actually do this type of thing. But you wanna cut it down to be able to extract out the parameters of interest, and then realize you have to go stochastic within that. You know? But you don't want just, at this level, there's not a lot I can do, because I can't see the variables of interest. All right, so this one is where we're going to gain predictions. This one is taken from long data measures, those ensembles over large periods of time. This is taking a look at your code that's going on. These two will also be affected strongly by your compiler, because certain compilers tend to favor one instruction over the other, and some of them are a little more efficient to making your code small that's going. So your compiler that's going on will affect these, it goes, and that one you're just stuck with. Although this itself can actually vary too, because most systems, because of our heat problem that's going on, we can't run the clock too high, but I can, for burst periods of time, overclock. So if I know this is a heavy load period, I can overclock it, increase the clock frequency for a brief period of time, and then drop it back down when it starts getting too hot. So I have a temperature dependent one on here. And this is another one that causes that same problem. That's also dependent on, did another process running simultaneous with me that's being switched in and out, did it overclock? Because if it overclocked recently, I can't overclock because it's too hot. And so there's a lot of things out of your control that are going to be in there, which is why the ensemble becomes important. So for us, this is largely what we're going to try to increase that's going on, and we're going to live with these other areas. But we do want to keep in mind where they're coming from and how we might be able to adjust those as well, you know, if we have any influence. Because we're going to talk about both hardware and software aspects, because a true design has to use both. Because the other advantage is the code can see all the static stuff of what's going to happen next. The processor can't see what's happened next, it hasn't loaded it, but it knows what the current variables are. If the code, right, the compiler takes a look at the advanced code and gives you some pre-warnings, now all of a sudden, the hardware can respond to those and prepare things in advance, which makes it more efficient, like pre-fetching data and things of this sort that goes on to reduce problems. So we call that cooperation between the two sides, hardware, software, code design. So when you hear those buzzwords about code design, that's what we're talking about. Somebody who really knows the hardware telling the software people what needs to happen so that those interlinks go on. All right, we feel good with timing. So what are we going to do with this? Once I have time, I want to figure out how much better it gets, right? So the first cut on this is Amdahl's law to calculate the overall speed up. Anybody remember Amdahl's law? No. Okay. easiest way to remember Amdahl's law is not to memorize Amdahl's law. So what you do, Amdahl was trying to say, hey, look, if I make an improvement to a system, there's an improved portion and an unimproved portion. So let's say the original program ran in t old seconds on the original processor. Now, I can split this up into two pieces. There's some fraction of the time that the processor would have been able to use the new cool improvement. So we'll just call that fraction f, because we just love reusing letters. Right? That means 1 minus f of the time it would not have been able to use it. Now for the original problem, it didn't get any speed up, nothing changed, so when you add those two together it still becomes t old. When we go to the new one that has that speed up, it encounters some speed up s. This is speed up overall, s overall, that one's just s, that speed up of that little subpart. So the speed up of the subpart is gonna commensurately divide this one, so it takes less time. So on the new system, this will take f times t old over s. We'll get a fraction of that time. Because if you doubled it, it'll have the time. But it only has the time where that speed up is used. That means 1 minus f of the time, it doesn't do anything. So you just keep that in mind. What happens then, speed up is, you take the slow one on top and you take the fast one on the bottom. That way, the faster the new one is, the larger the number saying how much it sped it up. Because performance is the inverse of time. Well, t old doesn't change, t new is this. But that's t old all the way through. I can cancel t old top and bottom. Okay. Substitute in, right? And I can, so on every term, I can cancel it. Right? See, I told you so. Hey, I reserve the right to make horrible jokes. My kids suffer with it, why shouldn't you? All right. So that's the Amdahl's law everybody loves and remembers. I submit to you that you can actually get a million varieties of this, and who cares? If you remember how it came in, it's such a simple idea that came in. What if I had two speedups that were both happening inside the system? I had some system F1, and I had a second one F2. And I have two of these different ones. So I've got speed up 1 and F2 times t old over speed up 2. That means this fraction, it's 1 minus F1 minus F2. Right? The fractions have to add up to 1. T old all the way through, I cancel it. Well, now you got the improved Amdahl's law form, right? With multiple ones, it just gets you 1 minus F1 minus F2, right? And then plus F1 over S1 plus F2 over S2, right? And people note this and they go, ooh, I can write that in summation notation. So you get 1 minus the sum of the f's plus the sum of the f, so the s sub I. People start getting very complicated looking formulas that they're all really proud of, right? And then people think, oh my God, I better memorize these. I better have the multi-form memorized and basic form memorized. And if you do that, you are wasting brain cells. It is a completely useless thing to memorize. Get the basic idea, and you're okay. Right? Now, this actually has, and so it's kind of a nice way to get a ballpark. Again, I give you that caveat, ballpark. And it's a ballpark because this cannot accurately tell you things under certain cases. Notice, I've made some assumptions here. Whatever the original problem time was, you're just dividing it up, and adding this extra thing in didn't incur any extra costs. Is that true? We already said, pretty much never. You add something else in to reroute things. If I have multiple cores, and I'm running on multiple cores, there's a cost to communicate. that if it was a single program, you wouldn't have to pay that network cost. Something else was added. Right? For instance, the network latency communication time that's going in. What fraction did that have? But the fraction of communication might depend on your problem size. Because there's a setup, and that setup might be using one distribution of instructions, and then the regular run type could be using a different distribution of instructions. So your breakdown frequency of how often it's used depends on how big the problem is. As it gets bigger, you're going to have a different distribution of things. You might even utilize that coprocessor differently. Right? So that frequency could change. So there could be extra pluses, and these frequencies could be problem size dependent. Right? Now some people say chuck the whole thing, and Gustafson's law is kind of a simplification of this that doesn't depend on problem size. But if you look at his equation that goes in, Gustafson's law is a pathetically simple equation. He just goes 1 minus f, and then he's got plus, his fraction over, and the speed up that's involved. But that's all he does, and he just says that's how you should measure speed up. But the real idea is not the equation. Who cares? What his assumption is Gustafson makes the following observation. He says, hey look, Amdahl's law points out that the non-speed upable portion is going to be a band limiter to you. And he says, hey look, so if you're stuck with that, you're stuck with that, so why sweat it? What we should say is not, uh-oh, I can't achieve everything I want. We should try to just rewrite it to see how much improvement can I make from here going on with the stuff I could take advantage of. Okay, and that's a very optimistic, positive way of looking at things. But honestly, that's really more how do you interpret it. It doesn't change. It's still, he's looking at a fraction of code and you're speeding portions up and things of that sort. Okay, right? So that as you speed up those things more, it's better for you. Okay, that's nice. But, instead of doing this, he's not worried about this portion of it, so he's just ignoring it. And yeah, he can put in problem scaling, but I can problem scale these too. To be very honest with you, I only use these ones as a ballpark anyway. So I'm always trying to figure out what I can do on these and what's an efficient area. And you don't use this to determine whether or not, it makes sense to speed up, period. What you try to do is you use one of these equations to figure out which one gives me the best speed up. Because it takes you a certain time to design or change the hardware or to change the compiler or whatever else. And it gives you a certain benefit. And this is really, honestly, all this stuff aside, this is really what the issue is. You get a measure of how much does it help things, and what does it cost monetarily to implement that fix, and that's your cost per performance breakdown, and then you want the best performance at the cheapest price. So, the problem with all of these ones is they don't include the cost portion, which is why we talked a little bit about cost leading into this. That you should always be mindful, okay, when I build this thing, ballpark, how much should it cost, right? We're engineers. And then we say, it's going to give me this amount of performance, how much does it cost to do it? How soon can I be done, my time to market? And if I think I can look better than my competition and sell it cheaper, then it's a good idea. And that's really where it comes down to. It make sense on all these? Okay, we got about 5 minutes left. So, if you guys have a little bit of time here, why don't we talk a bit about the labs area that's going on? Okay, now, fortunately I have found a bunch of videos that were recorded at my old institution where I taught these on YouTube, and I'm pulling them across to Canvas, so they should be available either now or pretty soon, depending on how long it takes to process stuff. Including 2 ones where I talk about the labs, so where it's going in. So that video should help you a little bit discussing them. Has everybody looked at the labs so far?
Yeah, lab one.
Lab 1. So lab 1 is like really darn easy. Okay? What I'm giving you is essentially exactly the labs I gave there. Master students would come in, and some of them had never seen, because it was a computer science and engineering, so I had some computer science people who came in who had just never ever seen hardware before. And they had never heard of a hardware description language. So that first lab, you should be like, dang, that's easy, right? Yes, because it was designed for somebody who had never hit things as it's going on. And I'm trying to, in one lab, give people enough that they can go, I know how to program, how do I get this in, right? If you look at lab 2, all of a sudden you're gonna be like, right? It will change drastically, okay? I want you to try to take a look at some of those areas. What we're building is Tomasulu's machine. I'm gonna give you a quick sketch of Tomasulu's machine so you get the idea. And I'll let you know the part that you're dealing with on that one. And I gave you, part of the reason why it's gonna look huge is because it's a big block of code that I gave and you have to modify certain portions of it. And I believe I've got videos explaining steps 3 and 4 that I found on the web, but I didn't find, these were students that recorded them and uploaded them. So evidently nobody recorded the second one, but the 3rd and 4th did get recorded. So I didn't even know it was happening, so it's just, but it's convenient now, so I'm taking advantage of it. So Tomasulu's machine basically works like this. We've got this whole fetching unit that's coming in. And it's going to be fetching things really crazy fast. And it's going to be trying to issue things. So we're going to do fetch and issue. Issue is often part of that whole decode thing. But we're going to do the fetch, decode, issue, large portion of that. And we're going to shove it all into this unit that's going to go get things. And it's going to build up a table. And on that table, it's going to carry some statistics. How far has it gone along? Has it finished this step? So it's going to track its progress as it's going. I would call this scoreboarding. It's kind of like if you look at a game, you see the team's names and you see what have they done at each time period. We're going to do this same tracking of where is the problem and is it held up, what's it waiting for. All this information we're going to do inside this fetching area. That's the last thing you're going to build. And there's a whole hour and something thing explaining that one in detail. So I'm not going to sweat that one too far. This one, when it does, it's got to issue commands to 2 things. Right? It's got to be able to tell when it comes in. Right? We've got a register file that stores all the data. So if you remember before, you had a register file, and then you send in an address, and it spits out whatever your data was as it's going on. Right? This one is no longer able to be that simple, and the reason is I'm going out of order. So if you think about your series of instructions, I could have like an add that's updating R2. And then I could be picking up R2 as the next one as an input and going somewhere else. But when that other one hasn't finished, the first instruction hasn't finished and the second one needs to use it, we need to flag, you can't just use the value in R2 here. You've got to wait for that other instruction to finish and get its answer. This is the whole cool idea of Tomasulu's algorithm, is he redirects, kind of like call forwarding, when you leave home and you forward your calls to your cell phone or whatever, right? That's going to become a worse example as time goes on, as people don't have hard lines. But the idea that you could send your calls somewhere else is the same idea. This one's going to have to say, hey, somebody else is updating me, so my value is no longer important. I have to know who that is. So it's going to have to track, am I any good? So a valid bit. And it's also going to have to say, if I'm not valid, who do you go to talk to get the correct answer? Make sense? So it's going to store that extra information. That one, again, I also have a lecture on that one. That should be the 3rd lab that you build it. All right? And it's going to have to give information of what is the data, or where do you go to find the data. This one is going to also have to communicate what you have to do, and we have this execution bit. Right? Now, this one is sending out, here's an instruction, here's some data, or something that will tell you where to get the data. That means every time it gets an instruction, it can't necessarily run it immediately. Right? Because it's got an instruction, and it might just have, whenever this data becomes available from this location, you can use it. So if it's not ready to run right now, we have to make it wait. How do we make things wait in a computer?
Bubbles. Like stalling.